should all be, well, thanks very much for Louis for the introduction, and thanks for giving me this opportunity to kick off. It's very exciting this seminar series for the Data Science Center. So as Louis said, I've joined like a couple of months ago. My work is mainly at the interface between statistical modeling and machine learning, and how two can help each other with a particular focus on sort of this aspect of trustworthy machine learning when we talk about things like uncertainty quantification, causal modeling, explainability, and so on. And today, there's a specific, very recent research project that I want to talk about. We'll kick off sort of a little bit with a broader picture about how causality, causal reasoning, and machine learning interact. This, of course, will be not at all representative for the whole field of causal machine learning. It's very much biased by sort of the kinds of topics that are directly related to my own research. Okay, so let's get started. So for a kind of example where machine learning does need statistical reasoning, we can look into one of the most prototypical examples of applications of machine learning, recommender systems, right? So recommender systems are used to personalize your online experience. They tell you which movies to watch, what news to read, who you should be friends with, and so on. And they can be very successful and bring insights. But occasionally, the way they can go wrong is even more insightful. And so here is someone searching for a laptop rucksack on Amazon, and finds this particular rucksack. So it's a bit of an old example by Bernard Sholkov, but sort of I think it's very insightful. And so Amazon's automated recommendation system decides to suggest to this user to buy a laptop to go with rucksack. And in some ways, this is sensible, as many previous customers have indeed bought these two products together. But it is clear here that the recommendation engine has mixed up the cause with the effect, right? So, and this is sort of very important ongoing research question, which sort of my group has been interested in, how to discover cause-effect relationships from vast quantities of observational data. And that is a challenge, as we'll sort of briefly touch upon, because there are many possible confounding variables in various data collection artifacts. Okay, so let's talk a little bit more concretely. So it's a kind of like the whole story here is to try to disentangle this correlation that has been discovered in the data sets mined by this Amazon's recommendation engine from the actual causation that will bring further insights. Okay, so let's talk more concretely. So what do we talk about when we talk about causal modeling and causal reasoning? So there are several different ways we can formalize this, but one of the most basic tools in causality is this object here called directed acyclic graph, or DAG. And so what is that? We have a bunch of random variables, and I'm thinking about these variables generically. They don't have to be scalars. They're just some groups of covariates themselves, potentially, within each of these nodes. And what does it do? Well, it captures a way to factorize the joint distribution of variables of interest, right? So basically just encodes this factorization of the joint distribution, where where the joint distribution is factorized as the conditional probability of each of the variables in each of the nodes given its parents. And then we tend to, these directed arrows in the graph, we tend to interpret them causally. So we don't have to do that, but it turns out to be an insightful thing. Okay, and so this is just specific factorization for the distribution that corresponds to this graph. You will notice here there is a y and the vector. This will become important later. It's not really important at this point. And so what does this do for us? Well, one can read off from this graph a number of independence relationships and conditional independence relationships between these variables. So for example, I can spot that x2 is marginally independent of x4, right? So that means if I look at those two variables in isolation, they're independent, but maybe if I condition on other things, they won't be. And a bunch of others. So I'm just sort of listing two here. Okay. So that is a DAG. That is our causal model of the world of the variables of interest. So DAG represents certain conditional independent statements. And conversely, if we have a set of conditional independent statements, that determines not really a DAG, but some kind of equivalence clause of the DAG, right? And so you can then think about various tasks you can do in causal reasoning. And the first one would be, well, to discover this object from observational data. So two fields of machine learning and causal reasoning, they have been developing mostly separately historically, but there is in recent years, or to recent 10, 15 years or so, there's a confluence of the two fields and lots of interest on how they can benefit from each other. Okay, so I can sort of have already hinted this. So there are two main sets of tasks we can do in causal reasoning. One is, well, let's learn what that DAG should be. I have some observational data, a bunch of these variables. I have to learn about what are the actual causal relationships. And then the second set of tasks would be causal inference. So let's say we assume a DAG or a part of a DAG, and we want to actually either test for the presence of causal effect, so just whether there's an edge in it, assuming the rest of the structure of a DAG, or actually quantifying the causal effect. So actually finding quantities that tell us about one variable, what happens to one variable if we intervene on another. And so in both of these sets of tasks in causal reasoning, machine learning has been successful here. Various parts of that. And I will give some small examples of it. And as I say, this is by no means representative of all different uses of machine learning in causal discovery and inference, but there are some examples. Right. So one of the basic things in sort of in the early days of confluence of machine learning and causality, so to say, is this idea of inferring causal directionality. So we have two variables, they're coming at us in a paired fashion. We will assume that one causes the other. We don't know which one causes which, and we want to essentially build a model as to what is the cause and what is the effect. So it's a kind of classification problem. You can imagine that I have a bunch of data sets of X and Y, and one label is X causes Y, the other label is Y causes X, and it can be total as such. And many machine learning approaches have been used in this context, including kernel methods, neural methods, and so on. Okay, so that would be kind of like the simplest possible thing we can do in causal reasoning. So then we can make it much more general and say, well, actually, let's from a whole set of variables, let's determine the whole DAG. So we've said earlier that it is this sort of set of conditional independence statements that determines a particular equivalence class of these DAGs. So how these algorithms usually work is by performing a sequence of these conditional independence tests. So I'm going to pick two variables, test whether they're independent, then I will condition another variable, test whether they're independent then, and so on and so forth, right? And there's a sort of a whole theory that can build on what do you condition on and so on and so forth. This is usually known as PC algorithm. Often these tests, these kind of hypothesis tests would make use of non-parametric testing tools that have been developed in machine learning community, things like kernel methods. And this is sort of my own way of entry into the field of causality, because I have been working on kernel methods for hypothesis testing for a while, and that led to things like conditional independence testing that then can be used as a plug-in method for these kinds of causal discovery algorithms. Okay, so that's the example of a causal discovery task. How about causal inference? So in causal inference, you could do things like quantification of these causal effects using tools called do calculus that is developed in causal reasoning. And so essentially what you're doing, you're appropriately adjusting regression. Often you would do 2 regression tasks, and that's why this is sometimes called double machine learning as well in the literature. So there's quite a lot of interest in that field of study. So there's kind of a sequence of regressions that you're doing in order to do these adjustment formulas, and it is pretty generic, this framework of double machine learning. So these regression tools can be any kind of your favorite machine learning tool. So that's quantification, and then you can also sort of go in this direction of actually testing whether there is an effect or not. So you assume the rest of the DAG and you test whether there is a specific error. And again, you have to go via this direction of adjustment formulas and do calculus in order to do some kind of reweighting of your test, of your kind of typical independence test. And lots of different kinds of machine learning tools are useful in this context. For example, you might need to do some weighting of your sample, and those weights can be estimated using time. Okay, so that's a brief overview of these kinds of different uses of machine learning in causal reasoning tasks. And so what we've set out to do in this project is to think about whether some kind of causal knowledge can actually be useful in a very standard machine learning task. A very standard supervised learning regression, some kind of typical thing. What if we actually know something about the underlying causal structure? Can that help us? Right? So in a way, causality is returning the favor to machine learning. Okay. So this is joint work with my amazing students based in Oxford, Shaheen and Jane. And I guess what is possibly interesting to mention here, Shaheen is funded by a European training network, an interface between machine learning and climate science, and so sort of is an expert both on machine learning and climate data. And indeed, a motivation for this work comes from climate models. So here is very simple DAG. So we have 3 variables. There's CO2 emission, there's some aerosol emissions, and there's temperature. Aerosols, what are aerosols? They are microscopic particles suspended in the atmosphere. They can be liquid or solid. And what they do is they contribute a negative radiative forcing by helping actually reflect solar radiation. And that tends to cool the Earth. Okay, but there are sort of lots of different ways this interacts with the climate system. However, the magnitude of this forcing represents essentially the largest uncertainty in assessments of global warming, with uncertainty bounds that could essentially offset global warming due to CO2 emissions entirely, or double it. Basically, we don't know much. And it is thus critical to better understand aerosols and to obtain better estimate of this link between aerosols and global temperature. Okay, so why did we draw this very, very simplistic DAG without any variables? Well, this is just kind of like a toy example, first of all, but you will notice here that there is a very specific structure here. There is no arrow between aerosols and CO2. So why is that? Well, often in this kind of literature, these two are considered to be independent factors driving global temperatures because they operate on very different timescales. So like weeks versus centuries, essentially, right? Of course, the story is not as simple as that. You know, they're of course affected both by human activity and so on. But let's stick with this very, very simple DAG for now. So what are we going to try to do? Well, we're interested in aerosols, and it's going to be a simple prediction task based on climate model data. So to generate some data based on these climate system emulators, not going to be real data, but we're going to try to build a model that predicts aerosols using temperatures. And there's this kind of like inherent anti-causal structure in the prediction problem because we're essentially predicting the cause from the effect. That will be easier. Good. Right. So yeah, so I've already said the story. So machine learning tools have been widely used to solve various problems in causal reasoning. Recently, we have been starting to ask different kinds of questions. Can causal models do something to help machine learning to return the favor? And here, what we're going to do, we will identify a very specific case where the knowledge of the underlying DAG actually can help improve performance in regression tasks. And what we will do, we will try to quantify the generalization benefit of that kind of causal knowledge. Okay. So when we were talking about DAGs originally, we were talking about just factorizing joint distributions of a bunch of variables, things like this. When we're doing supervised learning, when we're doing regression, we're interested in quantities that are based on conditional distributions. Right? In particular, if I assume that there is some sort of response here, y output, and then there's a bunch of inputs x, I might be able to draw a DAG like that, according to some background knowledge domain expertise. And I'm interested in reasoning about the conditional distribution of y given x. And what exactly you're interested in depends on your loss function. And if we care about the squared loss, we care about the conditional expectation of y given x. Okay? And lots of things I will say can be generalized further, but here we will focus on that particular setup. Right, so we're interested in regression, hence we are interested in estimating the conditional expectation of y given x. So what does DAG actually tell us about this conditional distribution? Well, there is something that's obvious. Well, it tells us the set of necessary covariates in X that still retain the probabilistic information about Py given X. So often you call this feature selection. So I'm going to try to find certain features such that if I condition on those features, my response is independent of everything else. Sometimes called the Markov boundary of Y. Yeah, and that is the obvious way in which we use a DAG. We can use that, right? In this example, this is highlighted in blue because if I actually condition on all the variables depicted in blue, the response is actually independent of the rest. So we can chuck them away, and we are not actually going to miss on any probabilistic information about Py given X. Okay. Yes.
What is include X for X?
So for Markov boundary, usually if you assume the Markov sufficiency, faithfulness, usually Markov boundary can read it off from a DAG very simply. It's the parents, children, and the spouses in a sense that they are other parents of the children. So X4 and X5 are there for that reason. Because actually, if we move them, Y is not going to be conditionally dependent of X4 given everything else because there's this spark here. Okay, so and that's kind of actually quite closely related to what we're talking about because we'll be mainly talking about these colliders, and it's the colliders here that matter, that actually put these variables into the Markov boundary. Okay, so is that everything? Right? Basically, we're asking, is feature selection everything we can do on the basis of that? Well, we know that Markov boundary is this minimal set that satisfies these properties, so it sort of it tells us we cannot have any relationships of this form, so we cannot peel extra variables out. But we can ask whether there are other useful inductive biases that are coming from the unused conditional dependence relationships. Is there more in the DAG that we somehow are throwing away when we then just take the variables in the Markov boundary and run random forest? Are we throwing away some information that's in DAG? And you can actually look at this specific graph and you can notice two more. Right? So exactly because of this presence of the collider, we know that Y is actually marginally dependent of X. But when I condition on x6, they become dependent. Yeah, that's sort of the nature of the collider. We'll talk more about the intuition behind that thing. So I have this marginal independence of y and x4, and that is something that is encoded in this DAG. It is not something that I would use in any way if I just take my selected feature set and run that. And then we'll basically focus in this talk specifically on how to use it. There's another one you can develop. So conditionally on x3, y is independent of x5. Also something you can read. These are kind of simple rules how you read this on the graph. It's not sort of too important to go through that now. But basically there are these two extra conditional independence statements. And the presence of these independence relationships inside really the Markov boundary is possible precisely because of this collider, right? This collider which is sort of this node that y, x4, and x5 are pointing, so they're kind of colliding in x6. And this has allowed for these spouses x4 and x5 of y to be inside the Markov boundary without actually being adjacent to y at all. Yeah. And as a consequence, you get these independent statements. Yeah, so it's a Jonas' question is exactly pointing at this aspect, right? So somehow colliders appear to be central to what we're studying here. And kind of like I'll just give this textbook example of what a collider is. So this is sometimes also called B structure. So basically we have three variables. These variables are marginally independent, but when you condition on something else, they become dependent. So they're common causes of something. And here the story goes, well, say I have a randomly timed sprinkler, and there's also whether or not it's rained. If I condition on wet grass, they become dependent, right? Because if I know that the sprinkler was off and the grass is wet, then it's likely that it has rained. So they have become dependent once I've conditioned on this third variable, right? Yeah, you can sort of come up with lots of examples like whether or not my alarm clock was broken, whether or not I've been abducted by aliens, pretty independent, yeah? But if you condition on being late for the seminar, they become dependent. Great. So,
There's a question on Zoom just saying, why is x2 not in the boundary for x4?
I mean, sort of a lame answer is really that you just have to look at this kind of sequence of conditional independencies, and it is true that if I actually condition on x1 and x3, y becomes dependent on x2, because all the causal paths from x2 to y flow via x1 and x3. So, and hence then you can then come up with this result that I mentioned that actually it specifies explicitly what Markov boundary has to be. It has to be children, parents, and spouses, for the lack of better term, parents of children, other parents of children. Good, thank you. Good, so yeah, we kind of established these colliders are relevant for us here, and indeed we will call actual method collider regression at the end. So we have this very simple proposition, very basic stuff. So it tells us that actually, if we're interested in these kinds of conditional independent statements within Markov boundary, that will be useful inductive biases for us to include in our regression. Well, then they are present in a graph in the Markov boundary if and only if there is a collider coming out of y. So it's sort of somehow they're the only kind of graphical structures that we care about. Okay, so we don't use it. So when we do this feature selection with whatever our favorite method, and then we plug the features into a random forest or support vector machine or deep neural network, we don't use these additional statements. So what can I gain from using these additional statements? And we will consider sort of the simplest possible example that's non-trivial, and it will be just this simple collide. So a lot of what we say in the paper can be generalized to more complicated DAGs that involve colliders, but here we'll just focus on this one, right? So there are two sets of covariates, x1 and x2, and there's a response of interest, and I'm interested in predicting y using x1 and x2. Hence, I have data sets of paired observations of x1, x2, y. And I just to emphasize again, x1 and x2 don't have to be scalar variables, just a collection of covariates that conform to this kind of DAG. So we aim to minimize the regularized improvement. So we have the squared loss, and there's some normalization term. So I want to learn this function that sends me from the product space of these two domains, or these two sets of covariates live. We will talk about the choices of this hypothesis space later. And if this is a setup, then I know that the optimal regressor, the function that actually minimizes the risk with respect to the squared loss, is just a conditional expectation. So I want to find this conditional expectation. But I have this graphical structure. It actually tells me something about the conditional expectation. So without loss of generality, I'm going to just assume that the marginal expectation of the response is 0. So that doesn't really do anything. Just, center your responses. So for simplicity, we assume that. Then I know this very simple law of total expectation. I know that actually, if I take my optimal regressor, which is by itself conditional expectation, and I find its conditional expectation conditionally on this x2 variable that is marginally independent of y, I will get 0 as well. Yeah. So there's a very clear restriction as to what the optimal regression function has to satisfy. It cannot be any function. It has to be a function that has 0 conditional expectation when I condition on x2. Yeah. So that tells us that if I have my hypothesis space, so that's a class of functions under consideration, I'm really interested in some subspace of it once I have essentially removed that conditional expectation. Right? So that's a space of functions, say L2 or RHS, or space of functions modeled by random forests or whatnot, right? That is looking at this kind of relationship where everything depends on everything. If I restrict myself to this kind of DAGs, then I'm interested in strictly a subspace of my original hypothesis. Okay, and yeah, so it's some very simple reasoning will tell you, for example, if this space is L2, so space of square integrable functions, then you can think about this projection as being orthogonal projection, and you can, as a matter of fact, take any regressor, you can decompose it into something that lives in the space, something that's orthogonal to it, and a very simple proposition tells you, well, whatever you've learned, whatever function you've learned, any regressor from any model, as long as you're working with hypothesis space L2, discarding this part will be beneficial. Right? So this is notation. It's not too important exactly the details, but the basic story, this generalization gap. So the difference between two risks, risk of a function before I've done the projection, risk after I've done the projection, is always non-negative. Okay, so there's a caveat, right? What's a caveat? Well, I don't know what this projection is, because projection actually involves taking some kind of conditional expectation, right? So if I actually want to do this discarding, I would have to first estimate what P is. Okay. And that leads us to this very, very basic kind of algorithm that is a double regression in itself. So it's a kind of two-stage regression. So first we'll do our usual stuff. We build our model. We regress from our covariates to the response. whatever it is. Then we do another regression that is actually estimating the conditional expectation of the function, one-side condition on x2 only. Okay. And that tells me what I need to subtract from my regressor, and I get a new regression. Okay. Very simple thing. You can do that for any model. Can be applied to any hypothesis space or any regressor. So the result previously I quoted, so that is for L2 space, but this algorithm is completely generic. Okay. What's interesting? Well, this step 2, it doesn't require any y. We don't care about y because having fitted a function at hat, we just want to fit this conditional expectation. So for that, we only need inputs. We need unlabeled data. So this naturally fits in what's called a semi-supervised learning setup. So if I have inputs with labels and lots of other inputs without labels. So inputs without labels will be helpful for this step 2 in the regression. Okay. So I'm gonna run through some of this a little bit quickly, but basically I want to briefly talk about a hypothesis space being an RKHS. So that basically tells us what if we're doing some kind of kernel method that operates on the data that conforms to that specific DAC, right? So why do we generally care about RKHSs? Well, I've been working on them for 50 years, so I care about them because of that. But a large number of theoretical tools are well established when studying the generalization properties of algorithms operating on these spaces. So we can make use of those tools to study in a much more precise manner how this kind of operation, this kind of projection will benefit predictive performance. And so, yeah, and they are generally very expressive spaces. So under some very mild assumptions, you can come up with these are producing kernel Hilbert spaces that are very big. In some sense, they are dense in the space of L2 functions. Right. So specifically, what we do here is we quantify precisely the generalization benefit of the projection. And sort of look something like that. So that was the gap between F hat and E F hat and the projection, assuming the true P. We'll have to estimate it as always. And it tells you essentially the lower bound on the generalization. Yeah. Right. So you will be improving if you know exactly your projection P, you will be improving on average at least by this much. Right. And there are some interesting things you can spot there. First, in the numerator of the bound, you have this thing here, which is the conditional mean embedding of the conditional distribution of both covariates given x2, right? So it's a kind of strange singular distribution, but nonetheless it has these kinds of quantities, can be represented by these kinds of quantities. And roughly speaking, intuitively, this norm becomes big if this relationship is more complex. So you can expect that you get the bigger generalization benefit if you have a more complex relationship between x1 and x2. Okay. We know that the lower bound is of the order 1 over n, right? So if you have large labeled sample size, we would expect that this projection operator actually does not help much. Right? So if you have a large data set, maybe you don't really care about this because what you regress in the first place is already pretty good. We know that typically risk itself also goes down as 1 over n, so it matches that rate. Okay, good. So, but if you're in this setup where potentially you have a small n and you have this semi-supervised setting, lots of unlabeled data, it could indeed be helpful. Good. So I will very show you some experiments. So I will very briefly talk about this. So because of this very nice structure of the RKHS, in fact, you can do something a little bit different. It is possible, given certain assumptions on what a space is, you can actually directly zoom in on the red space of functions and work with them directly. So it turns out that if this blue space of functions is an RKHS, the red one will also be an RKHS, just with a different term. So somehow I can specify that space and just work inside that. I don't have to do this algorithm with color looks for a function here and then projects. I can just look for a function here directly. And so this is what this new kernel looks like. And again, depends on these representations of conditional distributions. Again, it has this semi-supervised learning flavor, right? Because in order to find that kernel, I need to do some kind of estimation procedure that depends on these conditional distributions. It's a kind of regression, but with Hilbert space values. Then I get my kernel, and then I'll just do the usual thing, usual kernel method with that. So very important difference between that and our first generic algorithm is that I'm not really estimating conditional expectation of any given function. I'm doing this before doing any kind of using of the responses themselves. So in a way, you can do this operation before any responses have been observed. Yeah, and just looking through some of the experiments. So this is some synthetic example. This is like a big multivariate normal model. Not that big. I guess we look at higher than it's like that. But so I have three-dimensional x1, three-dimensional x2. Y is scalar. So they come from a multivariate normal model on which you put some nonlinearities in order to preserve the DAG structure. Not so important. And then you can look at like sort of different flavors of these algorithms. You can look at the original kernel method without any projection. You can do this projection after you fitted the function. You get some improvement in performance. And unsurprisingly, if you look at the space, the red space directly, you get even further performance improvement. And this is a pretty generic projection algorithm here. You can apply it to anything, for example, to random forest. You also see a little bit of improvement. Then you can kind of like look at some ablation studies about how the generalization gaps vary with different things, like, well, how much samples I have, well, it goes down, doesn't really matter if I have lots of samples. How many semi-supervised samples on label data I have, it goes up, very good, and so on. And like dimensionality also is some kind of surrogate for this conditional mean embedding, and you see it improving, generalization gap improves as dimensionality increases. Right, yeah, so the aerosol example, similar story, you see kind of like a little bit of improvement there. Importantly here, we look at different metrics as well. So mean squared error corresponds to the squared loss we care about in regression, right? But if you look at different metrics as well, you can see some improvements. And yeah, let me just finish there. So what did I talk about? I talked about how these collider structures in a causal graph give us a useful form of domain knowledge, inductive bias, that can be used within very standard machine learning setup. And you can think about this as in sort of the context of this paper by Bernard Scholkopf that talks about this anti-causal learning. And basically what this paper argues is that distribution of the inputs themselves, semi-supervised learning, if you will only be relevant for predicting the conditional distribution in regression if we are working in this anti-causal direction, if we're predicting cause from the effect, not the other way. And here we go further and we look at very specific example of provable generalization benefit when going in this anti-causal. And so, yeah, we'll stop there. Of course, you can talk about what's the different ways you can extend this and so on. And importantly, you can think about related problems arising in the topics of algorithmic fairness, for example, where it's not that you have a DAG that you know, but you want to enforce these kinds of conditional dependence relations because you want your regressor to be fair. So that's another application of this. Okay, let me stop there. There, any questions?
Time for one or two.
Yes. That's a great point, right? So it's in a way a question about whether we have all the variables that we actually need, right? So this DAG is a valid DAG, assuming we have observed these variables. Often when you write down these kind of causal models, you will have the variables that are observed, you will have the variables that are hidden. And that, of course, will change the story dramatically. So what we're assuming is that we have a DAG where everything has been observed. So, but it is certainly possible. Sorry? Yeah, there's no missing variables here because any kind of missing variables, if we ignore them from our DAG, it will actually change the structure of the DAG. So it's a very, very important assumption. Yeah, so no, that's a great point. So actually, discovering colliders is something very interesting inside these PC algorithms that are part of this causal discovery task that I talked about. And you can proceed in several different ways in discovering colliders. So essentially, usually what we do from observational data, if we don't have domain of expertise, is we run this kind of sequence of conditional independence tests that actually tell us what a DAG should be. And it's even a little bit more complicated than that, that we don't get specific DAG. Some of the edges might not even be oriented because there's like a Markov equivalence class that satisfies the same kind of conditional independence statements. And so, yeah, indeed, the algorithm would discover colliders.